on a bridge. So this is what I want to do today. I hope we'll be able to finish. If not, we will request for one more session. This content is a lot. I'm not sure whether we'll be able to do it in one day, but let's see. Let's see how far we will go. So there we go. We did uh, have a discussion on cracks, and we were able to go through that successfully yesterday. Unfortunately, I forgot to share with you these notes, but I will share them today after this session so that you can refer to them. Put today's date here, 21st. Of November 2023. So I want us to discuss bridges. So generally, when we talk bridges, bridges can be classified by their by several categories, just like water tanks. I'll mention just a few in passing by way of introduction. So bridges can be classified by their material of construction or structural system. Things misbehaving in the morning. Bridges can oh, can be classified by their material of construction. Sorry. I think this pad is getting old. But their material of construction or structural system. So if we look at the structural systems, we talk of that we could have bridges that are simply supported or continuous beam or etc bridges. Simple or they could be continuous. These ones can be made out of reinforced concrete, simple or continuous beam, column, made of reinforced concrete, reinforced. Usually limited to small spans. Range of economically spans below 30 meters. Okay, so maybe a good example would be the outer ring road exchanges. These are reinforced concrete. They are, I think, 25-meter spans, and already you notice that the beam is pretty deep. Then we can have them in concrete, but pre-stressed concrete. The pre-stressed concrete, you can do much larger spans. With pre-stressed concrete, you can do even hundreds of meters of spans with pre-stressed concrete. But a good example closer home is Nairobi Expressway. Most of our other bridges, the big bridges in Kenya, like the Kilifi Bridge, are also pre-stressed concrete. And bridges could be made of structural steel. This could also be composite steel concrete. Or purely structural steel. Okay. Composite, a good example is the Sigiri Bridge. But closer home, the road on the interchange just before you get to Wilson Airport. This interchange here on the former Mbagathi, let me say Raila Odinga Road. Interchange near Wilson Airport. It's a good example of composite. Okay, of course, steel bridge is like what we have next to our campus, the footbridge of a railway, yeah? Just neighboring there. Nairobi Railway. That's purely structural steel. Okay. Now, this is the first approach of classifying bridges. We talk of the structural, the material of the bridge. We could also have other structural systems, like we could have truss bridges. Please give me a minute, then I come back. The power is back. Oh, that's better, more quieter. So we were saying we could also have, sorry, could have truss bridges. Truss bridges are mainly done in structural steel. Because in the olden days they used to make truss bridges out of cast iron or out of timber or some other materials. But generally nowadays these are done out of structural steel, mainly done in structural steel. The G majority of the footbridges in Nairobi town and its environs. Okay, so most of the footbridges, I think it's all the footbridges basically are just structural steel. No, it's not all of them, but a lot of them are truss bridges and they're structural steel bridges. They can span fairly large spans. For small self weight, this is the main advantage of structural steel, that you can do large spans, especially if you're doing trusses. You can do fairly significant spans with a relatively lower self weight of the structure. The deck of the bridge can be on top of the truss, in the middle of the truss, or at the bottom of the truss. The deck can be on top of the truss, at the middle of the truss, or the bottom of the truss. Okay, so if you have your truss like that, say you have your bridge truss like that. I'll draw 3 of them. Sorry for the bad lines. So you could have the deck on top of the truss. The bridge deck could be placed there. Or the bridge deck could be placed at the bottom of the truss. I think the footbridge across the railway is this arrangement where we have a bridge deck at the bottom of the truss. And most of the footbridges also, I think it's this is the arrangement. But you could also have places where you have the bridge deck placed somewhere in the middle of the truss. So part of the truss is above, part of the truss is below. All these arrangements have been done, though this one is not very common. Because of connection challenges. If you have to connect the deck elements onto the truss, it's easier to, to connect from the bottom or from the top. Not very common. This is railway bridge, I think. It's like this. And it's a truss. The most important items that are of interest currently on this kind of bridges is the issues of fatigue and fracture. And corrosion. Important. Issues for these bridges. We have a suspension bridge. Deck is suspended on cables, which you know, it's suspended on some tension members that are tied to a cable. Bridge deck is suspended on cables. Closer home here is a Masalani suspension bridge. When I was a very junior engineer, I think in my first year of working, so I had basically zero experience. I sat in a design office that part of what they were doing was to check one or two small components of the Masalani suspension bridge. So I got to do the donkey work on those checks, but it wasn't the design of the bridge. The bridge had been designed. It was just one or two small items that needed to be checked, and that's what we did some few years ago. These structures, this type of bridges are relatively very light. Relatively very light is not good English. Let's just say relatively light. For the spans, they are able to achieve. These bridges have got a problem of slenderness. One of the biggest headaches of these bridges is slenderness. have a problem of slenderness. And might be prone to resonance under wind excitation. A good example of this is the Tacoma Narrows Bridge. Which basically collapsed not because of ultimate loading, but because of resonance. It's a really interesting structure. Generally, you have your channel that you need to cross, whether it's an ocean or what. You have your water line. You have large supports. Have large supports. Could be two, could be more, could be one, depending on the number of spans and the lengths of those spans and the length of the crossing. This supports, you would span a cable. You got your suspension cable. And you'd have your deck. You can draw it in a different color. What can we use? Which is this one. So you got your deck there. Because this deck would be supported by vertical elements, slender ones, because they're purely under tension. So they need to be supported to be hung from the cable. You've got your suspension bridge towers. That's your water. Okay, so that's basically how a suspension bridge would look like. I really don't need to sketch this because you guys have seen a lot of this. If you go onto YouTube, the beauty is that the era that we live in, a lot of information is available on these structures and documentaries on how some of them were built or whatnot. These are good content for you to watch. Now that we are mentioning these in passing, we might not be able to go into the details because they're extremely highly detailed, as you will see in your bridge design unit. Those who will do that in the coming semester. Cable state. And this also is a bridge that is the support system is cables, but the principle of load carrying and whatever needs to be checked is a bit different. So see here also the deck, suspended. cables arranged radially from the support tower. So once again, you got your channel. You need to cross. Put your towers. The bridge deck. To your water line. Cables that fan out of the from the tower to go and called cable stays. We got your bridge deck. You got your towers. It's the main challenge of this bridge. The main challenge of this bridge, you notice that the cable stay, since it's under tension, so it's pulling away from the joint. If you can remember your method of joints, it's under tension. You can say here, under tension. So if you look at this element here, it has to be under compression. So we will say this element here will be under compression. And bending, making it a beam column. There's high likelihood which is prone to failure, which is prone to failure, which is prone to failure, which is buckling. That's the main concern about this type of structure. So when you design it, you have to ensure that the deck element is not only an element that carries bending and shear, which is what we usually design the beams for the deck for and the slabs for the deck for. If I will have the opportunity to take you through bridge design, I will take you through these thoughts, maybe not to a lot of detail because it's a lot of information, but generally you find that the deck, you want to check it for bending mainly, shear, things like punching. But then when you have the deck as part of a cable stayed structure, then the deck is also under compression. So it makes the design a lot more critical. Our neighbors, Tanzania, recently, no, not very recent now, during the reign of, I think, the late Magufuli, they put up a nice cable stayed bridge, which has featured in quite a number of music videos from that end. Maybe some of you have been to Tanzania and have been to that particular bridge. It looks like it's a very nice, beautiful, slender structure. I haven't seen it in person. Maybe someday I will go there physically to see it. But that's cable stayed bridges. Then, and this list is by no means exhaustive, but I want to mention one more, and this is the arch bridge. From your early analysis of structures units, you remember that you must have gone through arches, how to analyze them and stuff like that. So this is one of the places where now that basic analysis of structures for arches will come in. So the main structural element is an arch in these bridges. The main structural element is an arch. Made either of structural steel reinforced concrete masonry, etc. Arches carry loading mainly in compression. And right shape can be made very slender. Slender. And very efficient. Okay. So again, just to take you back to your analysis of structures, those earlier units of analysis of structures, you remember that it is possible to have an arch that carries loading purely by compression. And maybe this was mentioned, probably this was mentioned to you in class, that the perfect shape for an arch is a perfect parabola. You see, when you load a cable with a UDL, it forms a parabola. Now, if you reverse that, it gives you the perfect arch. Which is a parabola. The cable is the most efficient shape. It takes the most efficient shape to carry the loading in tension. If you were to flip that, then it gives you the most efficient shape to carry loading in compression. And that will be pure compression. That will be the perfect arch. So that's why I'm saying, and for the right shape, that's why I've written here for the right shape, because for example, if you build a semicircular arch, you will not have, it's not a perfect parabola. So therefore, you will have a lot of the loading will be will be carried by the structure in compression, but you'll have some bit of shear as well. So that's why I'm saying here for the right shape. The right shape can be made to be very, very efficient and very, and therefore you can then do very slender structures. And this theory is basically learned from nature. You know, the egg, there's a direction you can hold the egg, and you know the egg, the shell is extremely thin, but you know there's a direction you can hold it and try to press it, and you will not break it. Even the fellows who lift weights and have very strong hands, they do martial arts and stuff, it's very difficult to break it from that direction. Why? Because nature has made the egg to be a perfect parabola in that direction to resist external forces. So it's in nature, the egg has been designed to be extremely efficient in terms of material. So you know, there's a lot of calcium that goes into making the shell. So if the shell was made thick, then of course the birds would need to spend a lot of calcium to produce one single egg, which would make it very inefficient for them. So nature has made it efficient that, you know, for a very thin shell, or very extremely thin shell, you can achieve very, very strong you know, container for containing the contents of the egg. So this this shape thing is a big thing when you're designing the arch. Of course, arches have been here have been used by humans for many centuries. You see, if you look at the old historical buildings, the Greeks used arches a lot. The Arabs used arches a lot. In fact, Arab architecture is, you know, it's predominantly arches. If you go to coastal towns like Mombasa or Malindi or Lamu, you find the arch is a prominent form that is used. Of course, closer here, you don't need to go far. If you look at the mosques, which is basically Arab culture, you see a lot of arches. So the arches have been with us for long, and they have also been used extensively for bridges. And they make extremely beautiful bridges. We could say a few more things about this, but I want to pause here so that we have an opportunity to look at some sample, not to detail, just for you to get a feel of the kind of loading that one would need to do on a typical bridge structure. And I want us to look at a very simple, very simple structure. This is a culvert, a box culvert, which is basically just a small, tiny bridge. Okay, so allow me to now just move straight away to bridge loading. But we put some bit of numbers, just a little bit of numbers onto this. So say bridge loading. Then you realize that there were too many things that we were supposed to cover in this course, such that we cannot achieve too much depth with them. We just have to go mentioning. Some of you will do a course on bridge design in the next semester. You realize that even that one semester is not enough to discuss one type of bridge design, from loading to designing the elements. Just one type of a bridge structure. It's very involving. So, or a bridge type. So, say just simple beam and column, kind of arrangement would be very involving. Without saying we're talking about arches, or we're talking about cable stayed or suspension or truss bridges or etc. So, or even composite bridges. So just this section is meant to start you off on getting a feel of what would go typically onto the loading, not analysis and design, just loading of a bridge structure. So I'll write some few notes. We'll try and push this as much as possible. If we can't finish today, we'll need something like 30 minutes in one more session, and we'll be done with this content. One of the most heavily loaded structure groups existent are bridges. This is especially true for road and railway bridges. That is, as opposed to footbridges. Okay, though it's very interesting when you think about how us as Kenyans, and I think by extension Africans generally, how we behave. You see, you design footbridges for people to walk on, and once the footbridge is put up there, some enterprising Kenyans, they see an opportunity for a market space, so they go and start arranging potatoes and mitumba and everything. The result is twofold. One, you're putting in a lot of imposed load, courtesy of the merchandise that you're putting there. Secondly, you're attracting more people onto the bridge to just be there as they try to buy whatever is there. So even whatever human beings loading that you allowed for then becomes exceeded. Then some also enterprising Kenyans, when the bridge has got a ramp, some Duthis use it. They choose to use the footbridge to cross, using Duthis. So then you start having vehicular traffic up there as well. It's a very interesting scenario. Maybe if we find some bit of time, we will talk a bit about it. Part of the reason for this is the obvious heavy loading. So okay, so trains and no, so rail My apologies. I had to pick that. It's some clarification for the graduating class, and I needed to respond to that. So now we proceed with the discussion we were having. So we were saying that road and railway bridge structures are the most heavily loaded generally. And part of the reason for this is the obvious heavy vehicles that they carry, and part of it is the extreme spans characterizing some of the bridges. As is with other loading on structures, bridge loading is determined on the statistics of past measured loads. No more phone calls until we finish the class. Oh, sorry, I have two. Yeah, now it's okay. It's one. So we were saying, as is with other loadings of structures, bridge loading is determined on the statistics of past measured loads for that type of bridge, for that type of bridge. So let's say we are building a bridge for a class A road, Mombasa Road, for example. How we determine the loading that will go onto that bridge is to say, traditionally or historically, what kind of vehicles and what kind of loads have been experienced on this kind of road. So we say 40-ton trucks. So that's what we design for. So that's what we provide. Bridges have got different, they're designed to fit the class of road, and roads have got different classes. So some classes of roads will be lower, and therefore the loading on the bridge would also be lower because the kind and volumes of vehicles that will be expected there will be less. I'll just mention a story. I can't remember exactly which part of the country, but it was Western, the place where they harvest sugarcane. And there was a bridge that was designed for smaller trucks. I think this was either early this year or last year. And then this company decided to pass there a truck that was obviously heavier than the capacity of the bridge. And what happens? The bridge just collapsed. So this company had to salvage their truck from the river, and then they had to redo the bridge, rebuild the bridge. Okay, so it's important to be aware that bridges are designed to loads that are historical. It's just like the way we say buildings are designed to earthquake loads that are historical or to live loads that are historical. If we're designing a class, we say generally what has been experienced as loading for class. Or if we're designing an auditorium, we say then what loading has been experienced for an auditorium before, an auditorium of this nature before. And then we use that loading. So it's the same thing with the bridges. But now I want to give you a small story so that you have it as food for thought as we proceed. A few years ago, there was a meeting of, I think, transport ministers or roads ministers or something for the East Africa community, and the minister for, I think, transport or roads or something for Uganda said they caught a truck at the border of Kenya and Uganda, and it had our trucks usually would be in the range of 40 tons, and they will not be expected to exceed that. So they caught a truck that had a total of 78 tons at the border. This truck had come from Mombasa port, come all the way to Nairobi, all the way, I think, to Malaba or something, passed on all bridges on that road. Now, what does that tell you? It tells you that you as the designer, this historical cannot be just what is given in standards. It's got to be historical that is applicable to your area. You'll experience this a lot, that for many years, when we design bridges here, we've designed them to the British standards. Of course, the Chinese, when they come and they are doing bridges for us, and the designs are done in their home country, and those designs are done to Chinese standards, to Japanese standards, or something. And then when they come here, maybe, I don't know whether those involved would have checked them against the BS standard or what, but this has been the tradition. Now you notice that these standards are written, and I'll show you what they say about loading. The loadings are written based on the experience in those countries where the standards were written for. So if it is a British standard, they took the behavior of road vehicles there, trucks there, loading there, and then they specified this. So us as engineers here now, we need to be vigilant and careful to say, are these loads applicable for us here with the kind of control that we have? So this is food for thought for any engineer who wants to basically go into the design of not just bridges, but roads generally. So I want us to spend a bit of time to look at what the BS, which is what I told you we have been using here for the design of bridges, recommends. So I'll write it as a question. What does, it's now past, it's no longer in place. What did the BS recommend? Two main load categories need to be checked when designing a bridge to the BS standards. Two main load categories. Checked. Designing a bridge to the BS. And I will add here, and by extension, the Eurocode now. These are HA loading. I'll explain what each of these are. And HB loading. The Eurocode might call them a bit different, but the principle is basically the same. Before I tell you what these loads are, the tradition has been like this, that you would define these two load categories separately on the bridge. So you take the bridge and load it with HA loading. And you take the bridge and load it with HB loading and analyze and get the member forces. And then you would pick the most critical of those. So if the HB loading gives you the maximum possible shear, then you take that shear value and design for it, for that element. Then if the HA loading gives you the maximum possible axial load, for example, on a column, on a bridge column, then you would take that reaction and design for it. So you would have two separate load conditions. Then whichever gave you the worst case scenario, that's what you would design for. Now, having said that, what is HA loading? HA loading consists of a uniformly distributed load, plus a knife edge load. I will tell you what that is. Simply referred to as a KEL. HB load on the other hand, it basically mimics the vehicle tires on the road. HB loading mimics the vehicle tires on the road. So consists of vehicle axle loads. We look at both. We look at both a little bit, so that they become clear. How they will look like. Now, beyond here, I will zero in on the HA loading. So let me show you very briefly how the HB loading looks like from the standard. I'll just show it to you. We will not put numbers to it, so that you are aware that that it exists. References. I don't know whether I can find this standard. Yeah, I found it. The 5400. I hope I can find it quickly. If not, we'll skip that, because you'll deal with that. Those who will do bridge design the semester, you'll dig into this quite a bit. So we don't need to bog ourselves down too much. I thought it would be nice to see how the tires are arranged on the bridge. And whatever this standard specifies is almost word for word what it's just been lifted that way and put. No, it's not word for word. I take that back. It's a bit different. The thought is the same on those tire loads, but the considerations are a bit different. Sorry about that. It's not the same as what is in the Eurocode. This is it. Sorry, I was looking at the wrong standard. So 5400, BS 5400 part 2 of 1978. Of course, this now is obsolete, but this figure you find similar in almost all the other design standards for road bridges. So what you see, and it's refusing us to scribble, but these things that are square, they represent vehicle tires. Truck tires, basically. Okay, so you've got two axles, and then you have a space, then you've got two axles. So two axles at the front, space separated by 1.8 meters. You see, it's if you think about it, it's like a truck with a double axle, and then the space, and then another double axle, then space, then another double axle. This is the thinking. So that's why I'm saying it mimics vehicle tires on the road. It has an overall width of 3.5 meters, which is it assumes a lane of 3.5 meters wide, and the vehicle of 3 meters width. And then on each axle, there are 4 tires, 1, 2, 3, 4. And whatever load goes onto that axle is assumed to be distributed equally to those 4 tires. Okay, so this, I will not go into a lot of detail for it. It's just, I just wanted you to see it so that next time you see it, you will remember that this figure I had seen before, and then when you do bridge design, you look at it to more detail, and it will make a lot of sense. It's not a difficult figure to understand and to apply on your bridge design problems. So this figure is referred to as dimensions of the HB vehicle. Okay, so I want to leave that at that point to say that we have mentioned a little bit on the HB, but I want us to see if we can put numbers to the HL loading and pursue it as part of this discussion. So I want to write here HL loading. So the HL loading. So the BS that we have just opened and looked at that figure 11, it specifies that the HL loading should consist of a uniformly of a UDL of 30 kilonewtons per meter, per lane. Per lane. And a knife edge load KEL of 120 kilonewtons per lane. Okay, so I want to draw a road section that has got 2 lanes, one going one direction and another one going another direction, so that then I explain to you how this load is applied. Consider this sketch of a road section. You put one lane you got one lane going that direction, so it's just 2 lanes. Let's assume that this road is bad line, but I will just leave it that way. Let's assume that these lanes are 3.25. Okay. So we will take the 30 kilonewtons per meter per lane. So we'll take that lane will be loaded by 30 kilonewtons per meter. So if the lane is 3.25 or 3.5 or 3, whatever, but each lane will need to carry 30 kilonewtons per meter as part of the HL loading. Of course, there's a limit to how many meters you can apply this before it starts reducing, but I'll not go into that because I'm just introducing this element or this concept. I don't want to say too many things, so then you lose your thoughts on it. So this is the UDL. It's applied on the lane at a rate of 30 kilonewtons per meter of the length of the lane. Okay, and then you have a knife edge load, which is a line load. So I'm trying to draw a line load here. So it's a load that is basically a line. It's a line load like that across the lane. Okay, and this is the knife edge load of value 120 kilonewtons. So that's what the BS meant when it talked about HA loading will have two components. One will be a UDL, which I've sketched for you, and the other one will be a knife edge load. It's basically an edge, a line load. So it's like you put a knife there, and the knife is then supporting 120 kilonewtons. That's why it's called a knife edge load. It's just line load. The knife edge load refers to a live load across the road. So I want now to pick this loading and take it into the context of a box culvert. I want to pick this loading, just the HA loading. We said we will not deal with the HB loading. Hopefully those who will do bridge design in the next semester, they will have the opportunity to do that. Okay. But for now, I just want to make us, and this is meant to be a demonstration so that you get a feel of what would go into the calculation of just loading without analysis. Because we need to load correctly, then we need to analyze correctly, then we need to design and detail correctly. The crack calculation that we did is an extract of the design phase. Okay. I thought to mention to do that because we discussed water tanks. So as part of a calculation that could be applied to water tanks, I lifted that and thought to present it. So now I want us to start looking. We'll probably not finish today. I want us to start looking at this loading on a box culvert. So consider, as I say, right here, example of HA loading. We want to work with a 2 by 2.5 by 2 meters high box culvert. So basically it's a twin cell box culvert, and I'm making an attempt here to draw it in 3D. Always when you have a 3D image of whatever you're trying to design, it's a lot easier to follow the rest of the concepts. So I'm making an attempt here to draw the box culvert in 3D. So it's got two cells. Okay, and of course the box culvert has got a length. Box culvert has got a length. This box culvert is supporting a road. So of course there's a road there. One lane goes that way, the other lane goes that way. It's the vehicles going that way. And of course, water goes through the box culvert. I know I did mention this a bit earlier when we talked about the crack problem. You need to remember that we will design a strip that is 1 meter wide. But before we design that strip, we have said we have two lanes. If we assume that those two lanes are 3.25, then we will have a total length of the culvert. We can assume minimum length. I'm using the word assume because it's not always like that. And I will not go into that detail. Okay. So this, let's assume it's the two lanes, so it's 6.5 meters. We did mention that in the design of a box culvert, we usually consider a meter width, 1 meter width. We usually consider 1 meter width element. So I will sketch that element as well here, so that then we don't need to imagine it too much. That's a bad line. One meter width. Of culvert. Is considered for design. It's considered for design. An elevation of this section of this culvert will look something like this. It's not very neat, but we're saying that these openings are 2500. So width here is 2500. And this one here is also 2500. The height of the opening is 2 meters. This height here is 2 meters. We're saying thickness, let the thickness of the top slab be 350. Bottom slab as well, 350. Let the vertical walls be 300. So with this definition of the box, we can ask, so what are the loads? We can ask, so what are the loads? And before we answer that, I want to start from where you know. So I say aside. In reinforced concrete design, for normal buildings, the ultimate limit state load combination for dead load and live load is design load for 1.4 dead load plus 6 live load is to the BS. Of course, the Eurocode numbers change a bit. I think 1.4 becomes 1.35 and 1.6 becomes 1.55 or something like that. But just for continuity of thought. Now, with this recap, we can say now for bridges, the BS specifies for the ultimate limit state load combination design load is equal to, I'll explain what each of these are, 1.15 EL plus 1.75 superimposed dead load plus 1.5 earth pressure plus 1.5 live load. So what are these? EL is the normal dead load, e.g. the weight of the concrete, steel, etc. etc. So this one is the normal dead load. E.g. weight, the concrete, steel, etc. A superimposed dead load superimposed dead load includes things like road surfacing, soil above structures, etc. etc. I want to draw your attention to this factor of safety for dead load, or what this standard calls dead load. You see, it's very small. Basically, this standard says you only put 15% on top of what has been calculated as the dead load. So if the self weight of the concrete, for example, is say 20 kilonewtons, we only add another 3 kilonewtons on top. We add only 15% of it. Why is it that this factor of safety is small? It's because the material of the structure itself is not likely to change much during the service life of the structure, which usually will be 100 years. I'll repeat. The normal dead load for bridge structures is given a small factor of safety because the material of the structure itself is not likely to change much during the service life of the structure, which is usually 100 years. However, if you have your box culvert there, now in elevation, and maybe it is buried a bit, you find sometimes the road is raised and the box culvert is somewhere further down. So it's buried a bit by soil. And then you have the road surfacing. These two are likely to change significantly during the service life of the structure. Because every few years, we put a new road surface. We resurface the road. We resurface it. So easily, we started with a surfacing that had been done of 50 millimeters. In the next maybe 20 years, you find that the surfacing now that is existing there is maybe 3-4 times that. So because of that, that's why there's a different category of dead load. They're still dead loads. They're still dead loads, but they are categorized as superimposed dead loads. These are dead loads that are likely to change significantly during the service life of the structure. That's why they're categorized separately and they're given a very large factor of safety, 75. The EP refers to the lateral earth pressure that is put onto the structure. Due to the retained soils. I didn't finish what I was writing, and these two are likely to change significantly during the service life of the structure. During the service life. Okay. So EP is the lateral earth pressure due to the retained meet again next time. Thank you.